Hello and welcome back. Today we're going to talk about the concept of power absorption and generation in AC circuits, that is circuits that are excited by sinusoids. If you go back to our previous discussion on phasors, you see we never really talked about the power absorbed or generated by those circuit elements, only how to find the voltage and current phasors of those circuits. So today we're going to dive into the concept of power in AC or sinusoidal circuits, because there are some subtleties there that we really need to make sure we understand. So in this particular example, we're going to have our generic linear circuit element. It's going to have a current forced into it of Im cosine omega t plus phi. So it's got a generic amplitude Im, the frequency of operation is omega, and of course there could be a phase shift, we'll call it phi. If you force that current into a linear circuit element, then in general I expect a voltage to be created, plus to minus, so we're satisfying the passive sign convention. And the magnitude of that voltage is going to be Vm cosine omega t plus theta. They're going to have a magnitude Vm and have a phase angle theta, which is going to be in general different from phi. So now we're interested in the power absorbed by the circuit element. So the definition of power, electrical power, is V times I. So we simply take the current, and it's directed into the positive terminal, and the voltage, and multiply those two together to get the instantaneous power. The instantaneous power is the power absorbed at any particular instant in time. So we multiply those two together. Now, to simplify, we see that, of course, we're using sinusoidal signals here. So these are both cosine waves. And so if you go and recall from your trig the cosine product formula given there in the box, then we can simplify, and we see that the instantaneous power in the situation that we have drawn here at the top of the page, the instantaneous power is 1/2 Vm Im cosine 2 omega t plus theta plus phi plus 1/2 Vm Im cosine theta minus phi. Now observe here that we have this part on the end. Let's look at it first. We see, of course, Vm and Im are simply numbers. These are the numbers that we get when we do our phasor analysis of this particular problem. Theta is a number that we compute, phi is a number that we compute, so Vm, Im, theta, and phi are really all constants. So this term out here in the end just evaluates to a number. And then on the left we have this part, which we see does involve a function of time. It's actually got it's a sinusoid, but the frequency here is 2 omega. Recall we excited the system with a frequency of omega. Of course the voltage is also going to be omega, but we see we have an oscillating power part which is operating at a frequency of 2 omega. So if you want to actually plot this, maybe get a better idea of what's going on, so we have the same scenario here, and here I've simply taken a couple of just voltages and currents, and you see they both have a magnitude of 1, and they have a slight difference between theta and phi, and I just made up some numbers so we can see an example. And if you take these two waveforms and plot them together, you get the chart here on the right. Now remember, this is simply a constant. Vm, Im, theta, and phi are constants, and this part corresponds to this little dashed red line. And then we have this is an oscillating part, and it corresponds to the blue dots. Now notice over on the left that we started with a frequency of omega, and you notice that the oscillation over here in blue on the right hand side is actually oscillating at 2 omega at twice the frequency. So if we, just to put some numbers on it, we're at 60 hertz as our waveforms for our voltage and current, we'd see an oscillating power part that's operating at 120 hertz, and that oscillation is riding atop, if you will, this value, which is given by 1/2 Vm Im cosine theta minus phi. And so this is the relationship we need to remember for instantaneous power in the scenario of a generic current and a generic voltage in a linear circuit element. Okay, so let's go and look at another view of the power, and that is the time average power. But before we do that, we need to define what time average is. The time average of a periodic function, so we're going to have a periodic function x of t, and if it's periodic it has to have a period, and the period is going to be t. The time average of this is going to be 1 over t, that's 1 over the period, the integral over a period. So we're going to start integrating at a time t0, and we're going to integrate up to t0 plus t. So that's integrating over a period, and over that period we're going to integrate our function x of t, and then we're going to call it x of tau d tau in order to keep track, to keep the t separated from the taus. And so you're probably familiar with arithmetic averaging, where you add up a bunch of numbers and divide by the number of numbers. Well, a time average is a really similar concept. You see that we're adding up a function, and we're adding it up over time. And how much of it are we adding up? We're adding up a period's worth, and therefore we need to divide by a period. So we add up a period's worth of a function, and then we divide by a period, and that will be the time average. So this is the definition of a time average of a periodic function. So let's take that and apply it to the scenario of instantaneous power. So, and this is going to give us the time average power. So we have the same scenario as before. We have our current being directed into the positive terminal of our linear circuit element, and they're all generic. Im cosine omega t plus phi is the current. Vm cosine omega t plus theta is the voltage. And if you plug that into our definition from the previous page on time average power, then we get the result here at the bottom of the page. Before we dive in, let's remember that omega is 2 pi f. Therefore, f is going to be omega over 2 pi. And of course, f is actually 1 over t. And then that means t is going to be 2 pi over omega. And so coming into our definition, 1 over t is out front, all right, which is right there. And then here is the t. And then inside, underneath the integral, you see the instantaneous power. So this is the time average of the instantaneous power. We are integrating over a period and dividing by that period. And when you do that, let's look at more carefully at what's going on inside. Remember that this portion out here is simply a constant, so we're adding up a constant a whole bunch of times and then dividing by that amount. So we can just pull it out because you're just going to get that same number again. And then we can bring the 1/2 Vm Im out front if we want, and we're left with an integral of 2 omega tau plus theta plus phi. Now look that we are integrating over t, but now we're oscillating at twice that frequency. So really what we're doing is we're actually integrating over 2 whole periods, but it doesn't matter. If you integrate over a period, 2 periods, 4 periods, a million periods, as long as it's an integer number of periods, and you integrate a cosine over an integer number of periods, and this term here is going to go to 0, and then you're left with the result that we were looking for, and that is the time average power of a circuit element in the presence of sinusoids is 1/2 Vm Im cosine of theta minus phi. Remember, Im is the magnitude of the current, phi is the phase angle of that current, Vm is the magnitude value of the voltage, and theta is the phase angle of the voltage. So this relationship at the bottom is the time average power absorbed by a circuit element when it's being excited by sinusoids. So with that, we have 2 relationships, one for instantaneous power and one for time average power for sinusoids. So let's do an example. So the first scenario we're going to have here is we are going to have our generic current being forced into our generic voltage. So Im cosine omega t plus phi is being driven into our resistor, and it's going to give rise to a voltage. So let's redraw the circuit, put it in phasor form, and remember that this has really got an impedance of R angle 0. So I know the voltage phasor that exists, the voltage that will exist out here is going to be I phasor Z. Well, I is Im angle phi, and then our impedance is R angle 0. And so when I do the math, I get IMR angle phi plus 0, which is simply phi. Now remember, this is the voltage phasor, so remember this is right here corresponds to Vm, and this part here corresponds to theta. So now we're ready to find the instantaneous power. The instantaneous power is 1/2 Vm, well Vm is IMR, times Im, so put a squared there, cosine of 2 omega plus theta, theta was phi, plus 1/2 Vm, and Vm is IMR times Im cosine of theta, which is phi, minus phi. And then simplifying this, we'll get 1/2, well, we can just leave that the way it is, 1/2 Im squared r cosine 2 omega plus 2 phi, plus, and then we see cosine of phi minus phi is the cosine of 0, so this term here evaluates to 1, and we're left with 1/2 Im squared r as that term. And so we see what we expect. Here we have some constant part, and here we have an oscillating part, and notice the frequency of oscillation is twice the frequency that we started with. Now we also want to find the time average power. The time average power is simply going to be this term right there, 1/2 Im squared r. Now if you think back to the DC case, remember we saw for a resistor, the power absorbed by a resistor is I squared r. Now in the case of a resistor with a AC voltages, so we have AC voltages and currents that are exciting our resistor, the time average power, so it's not the exact same thing, this is the time average power in the presence of a sinusoid at a resistor. It's also I squared r. You also have I squared r, but you see that the I squared r has this 1/2 term out in front, so don't forget to put that on there, 1/2 Im squared r. Let's do another example. So let's take a normal ideal capacitor and let's direct our current into it and see what happens in the power sense. So remember that this is really going to be minus j 1 over omega c, or you could also write it 1 over omega c angle minus pi over 2. So what is the voltage that's created when I direct this current I into our impedance? Well, the current is Im angle phi, and our impedance of our capacitor is, I need the polar version, 1 over omega c minus pi over 2 radians, and that's ohms. And so we're left with Im over omega c angle, and that's going to be phi minus pi over 2. And with these values, we can now find the instantaneous power. The instantaneous power in this case is 1/2 Vm. Well, Vm is Im over omega c times Im, so put a squared, cosine of 2 omega plus theta. Well, theta is phi minus pi over 2 plus phi, so that goes there, plus 1/2 Vm, which is Im squared over omega c times Im, cosine theta. Theta is phi minus pi over 2 minus phi. And then we can look at this and we see that we have cosine of phi minus pi over 2 minus phi. So this is the cosine of all this part evaluates to the cosine of minus pi over 2, and all of this goes to 0. And so we see the instantaneous power absorbed by our capacitor is this oscillating part, and it oscillates again at twice the frequency that we started at. All right, and now we can find the time average power. The time average power is simply going to be this value out here, and so the time average power of a capacitor is 0. The time average power of a capacitor is 0. There is no real power, useful power, average power absorbed by a capacitor. All a capacitor has is simply an oscillating power. And what we have is a capacitor. Remember, a capacitor stores energy in an electrostatic field, and that energy is an absorbed power, but then that energy can be retrieved again. And so we see for an ideal capacitor, what you have is that you put energy into it, you store energy in the electrostatic field, but it's a cosine, and cosine is symmetric about the 0 axis, so that energy is given back to you. A capacitor absorbs and generates power, and it gives it back to you. And on average, the capacitor will not use all that power that all the energy you put into a capacitor will return back to you. So there is none that is purely absorbed or turned into useful work. Let's do another example. So now let's look at the case of the current being driven into an inductor, and this works the exact same way. Remember, this is j omega L, or it is omega L angle pi over 2. So I can find the voltage out here. The voltage is going to be the current Im angle phi times the impedance. The impedance is omega L angle pi over 2. And so when I combine those together, Im omega L angle phi plus pi over 2. And remember that this has to be equal to Vm angle theta. So we see that theta is really phi plus pi over 2, and Vm is going to be Im omega L. So now we can plug it into the relationships that we have. The instantaneous power of our inductor is 1/2 Vm, well Vm is Im omega L, times Im cosine 2 omega plus theta, which is phi plus pi over 2, plus phi, so we can put a 2 there, plus 1/2 Vm, which is Im omega L, times Im cosine of theta. Theta is phi plus pi over 2 minus phi, and then we can take this last term and look at it, and we see that this really evaluates to cosine of pi over 2, which means all of this goes to 0, and the instantaneous power absorbed by our inductor is 1/2 Im squared omega L cosine 2 omega plus 2 phi plus pi over 2, and that's it. So the instantaneous power is simply going to be a cosine operating at twice the frequency that we excite the inductor with. And remember, the cosine is symmetric about the 0 axis. So all the energy you pump into the inductor, you get back out. The inductor stores the energy in the electromagnetic field, and it will return it to you. And then we see the useful power, the real power, the time average power. This is the power that actually lights the lights, turns the motors, heats the room. This is the power that's tangible. It is simply 0. There is no real average useful power absorbed by an inductor, an ideal inductor. So if you go back and look at the previous examples, the capacitor and the inductor have 0 real time average power, and then the resistor does absorb real or useful or time average power. Let's do another example. So here we have a case where we have a voltage 4 cosine pi t over 6 volts, and it's being driven, it's placed across an impedance of 2 angle 0. So we need to find the current. We're looking for the power, so we need the passive sign convention. So I'm looking for this phasor, and I always begin by putting my omega up in the corner. Our omega is going to be pi over 6 radians per second. And so now I can find what I is. The I phasor is the V phasor divided by the impedance, and our V phasor is 4 angle 0 volts, and then our impedance is 2 angle 60 degrees ohms. Now I know that the angle of our impedance is really supposed to be in radians, but I'm just going to keep it in degrees mode to avoid having so many pi's floating around. And so our current phasor is 2 angle minus 60 degrees, and that'll be amperes. So the question is, what is the instantaneous power in our impedance here? So the instantaneous power is 1/2 Vm. Well, Vm is 4 Im. Well, Im is 2 cosine of 2 omega. So that's going to be pi over 3 times t plus theta, and theta is 0, plus phi, which is going to be a minus 60 degrees, plus 1/2 Vm, 4, Im, 2, cosine of theta, which is 0, minus phi, which is a minus 60 degrees. And so we evaluate this, and we will see that we end up with the instantaneous power is 4 cosine pi over 3t minus 60 degrees plus, and over here we have the cosine of 60 degrees, and this evaluates to 1/2, and so we end up with simply 2, and the units for this will be watts. And the time average power in this load is going to be just this part out here, which is 2 watts, or if you want to verify that, we can put it in a formula: 1/2 Vm Im cosine of theta, 0, minus phi, which is a minus 60 degrees, and we will end up with 2 watts again. So this particular load is 2 angle 60, so this is actually in quadrant 1. So this load 2 angle 60 lives in quadrant 1. That could be represented by a resistor and an inductor, and we know from our previous discussion the inductor doesn't absorb any time average power, so this 2 watts comes from the resistance part of this inductance up in quadrant 1. Alright, so to summarize, given a circuit element with sinusoidal voltages, that is, we have a current which is Im cosine omega t plus phi, so we have a generic magnitude Im and an arbitrary phase angle phi, and since it's a linear circuit element, I expect a voltage of the form Vm cosine omega t plus theta to result, so we have a magnitude of Vm and a voltage phase angle of theta. Then the instantaneous power is given by this formula right here. It consists of a part which is a constant and a part which oscillates at twice of the frequency that we excited the circuit with. And then the time average power, this is the power it turns out does the real work, that does things, the tangible, physical. The time average power is given by 1/2 Vm Im cosine theta minus phi. Vm is the magnitude of the voltage waveform, Im is the magnitude of the current waveform, theta is the phase angle of the voltage, phi is the phase angle of the current. And so here are the two relationships that you need to commit to memory, and this is again for the situation of a linear circuit element being excited by sinusoids. So we'll come back next time and we'll look at more power in sinusoidal circuits, and we'll define a few more terms and get some alternative viewpoints, and then we'll be ready to solve some very practical problems that occur in practice. See you next time.